let's see. Yeah, module 2 include the chapter 2, 3, and 4. Okay. So yeah, module also 5. So all these chapter 2 to 5 basically are related to the processes, and the module 3 going to be somehow related to the memory management. So I organize these so each module may include different number of chapters. Okay, so just let you know about this. Okay, so let's continue with the chapter 3, which is also the module 2B. So module 2A is chapter 2, 2B is chapter 3. So far we have talked about the scheduling for the processes, and we talk about the various different scheduling algorithm. Some of the scheduling algorithm is actually basically for the batch system, and some of the scheduling algorithm is for interactive system. So the scheduling algorithm we have talked about are Fifo, shortest job first, and shortest remaining time first. Okay, so it's a Fifo, shortest job first, shortest remaining time first. So actually, shortest remaining time first is basically the same. It's pretty much the shortest job first, except shortest job first is non-preemptive. So which means the scheduler will not remove the processes that's currently in the CPU. Now, shortest remaining time first basically means every time when a new processes come in, the scheduler going to compare the new incoming process with the process in the CPU and check which one has the shortest remaining time. So whether the incoming actual process has the shortest CPU time or the current process in the CPU. So whichever actually has a short CPU burst will get the CPU. Okay. If the incoming process actually has a short CPU time, then the scheduler operating system gonna preempt and kick the current process out of the CPU and allocate the incoming process. So, and then for the interactive, processes, the main actual scheduling algorithm is called the round robin. So the round robin basically, the scheduler does not differentiate any of the process. They're gonna treat the scheduler gonna treat all the process the same way. Okay, so what the scheduler gonna do is it can actually allocate, a certain amount of time. It's called the time quantum. Okay, so the time quantum is a period of time, so each process can, execute once they grab the CPU. Okay, so all the process gonna execute, with the same time quantum or less, and if the process is actually finished its job before the time, before the end of the time quantum, then the process is going to quit earlier than one time quantum. Otherwise, it's going to take pretty much one time quantum. And then once the process finishes job, and then the scheduler is going to allocate the next process. And next process is going to execute for another time quantum. And then the scheduler is going to actually replace with yet another process. So all the process is going to take a turn to execute. Now, one of the actually performance measurement is the response time. Now, normally, the CPU time, the CPU total CPU time is also important, but also for the round robin, I think the response time is very good because no matter how many processes you actually a system is actually running. So then every actual incoming process is going to be responded very quickly. It's all, but it's depend on how many processes we are talking about. So for example, if I have three process 1, 3, process 4, and this is actually the time, and then this is each time period is a time quantum. So the scheduler going to basically allocate a process 1 for just one time quantum, and then allocate process 2, 3, and 4. Now, if a new process actually join, so I don't know when the process going to be joining, but so for example, if the process 5 join at this particular time, okay, in the middle of some time, okay, so initially there are 4 actual processes. They're going to take turn. So then when process 4 finish one time quantum, then the scheduler going to actually schedule process 1 again, and then process 2 again, and then process 3. Now, while process 3 is actually executing, and then process 5 just joined, right? Process 5 just joined the team. But within the time quantum, the scheduler still continue to actually allow the process 3 to finish the job. And then after this, process 4 going to be actually in play. Once process 4 complete the job, and then starting from this moment, now we have 5 members in this club. So then the next one going to be process 5. So from the time when process 5 join these, actually enter the ready list, okay, to the CPU actually respond to process 5. This is actually response time. And response time is normally very quick. It will be fewer than a complete cycle for all the processes. So it's not, even though process actually 5 join over here, the response time going to be like this. Okay. Okay. But it will not more than a one complete cycle for all the processes. Okay. So then now the cycle going to start with 5 processes: P1, P2, P3, P4, P5, P1, P2, P3, P4, P5, until one of the process just complete the job and quit. And then the number of processes are going to be reduced to 4. And another process quit, a number of processes reduced to 3. So, but however, as far as these processes are still running, then the scheduler going to actually evenly allocate the CPU time. So each process going to get the same amount of time to execute. Okay. So that's basically, that amount of time is called time quantum. So response time is pretty good. Now, what about the total CPU time? The total CPU time is probably not as good. But however, one thing you need to realize is that for round robin, if a process is a small process, then normally the process gonna finish the job very quicker than a long process. Let's take a look at this diagram again when we talk about the performance. Let's see. Yeah, this is actually the diagram I just used. Okay, so the process 1, the total CPU time is 4. Process 2 is 4. Process 3 is 2. Remember, we talked about this example. And the time quantum is 1. Okay, the time quantum is 1. Now, in this case, let me actually erase. Okay, let me just erase all these drawing. I can actually start this one again. Where's my mouse? Okay, that's probably is the quickest way to remove that. Okay, so in that case, process 4 requires 4 time quantum, right? Okay, 4 time quantum. And process 2 requires 4 time quantum, and process 3 requires 2 time quantum. Because time quantum is 1. So what's the total, actually, the CPU time that it takes from the beginning of the process to the end of the process? So it's 9. Now for process 2, if process 2 arrive at the same time as process 1, and the process 2 gonna be also gonna be 10. And the process 3, if it arrive at the 0, but finishes at 6, so the total time is 9, 10, and a 6. So process 3 is, has a short CPU burst, so it's finished. It's actually complete earlier. So the total CPU time is smaller than the other two. So in general, the round robin is pretty fair, right? It doesn't matter who you are. I gave you same amount of time. So as a consequences, that the process with a short CPU burst will normally finish earlier. Okay. Now, the response time actually is very good. However, the performance of the round robin depends on 3 facts. One is the time quantum. Okay, the time quantum. The other one is the context switching time. Now, I mentioned the context switching because I did not mention that in most of the case, because in round robin, typically you cannot ignore the context switching time, because for round robin, typically the time quantum is relatively small. So normally, the time quantum is like from 10 milliseconds to 100 milliseconds. So in 1 second, the scheduler gonna switch, gonna actually do the context switch many times, couple of hundred to actually couple of thousand times. So you're gonna switch back and forth for about 100 or 1,000 times. So even with a small actual content switching time, because you have too many content switching time, too many content switches. So that's why the content switch time is not ignorable. So that's why the performance is also related to the content switching time. Okay, and also it's depend on the performance of the round robin is also depend on how many processes are competing for the CPU. If there's only one process, it doesn't matter, right? Even though you say I'm using the round robin, it doesn't matter because once this process complete the one time quantum, and the next time is the scheduler going to still allocate this process, right? Because there's only one process. Now, if you have a two process, now you can imagine that the two processes going to share the CPU. So because it's a fair actually scheduling algorithm, so I can assume that the two processes going to actually divide the CPU times. So each process is going to only take like 50% of the CPU time. Does it make sense? Now, if you have a three, then the same process, the three processes going to share the CPU. So each process is going to get 1/3 of the CPU time. And if it's 4, it's 1/4. If it's 5, 1/5 of the CPU time. Now, that's basically the general analysis. But if you actually think about the context switching, then the story is going to be slightly different. Okay, so now let's take a look at these different scenarios. Now, the first scenario, we actually ignore the context switching time. So the context switching time is 0. Okay, so then if you actually the process complete the CPU, okay, and then the process for whatever reason just quit the CPU waiting for something else, and then the process actually requests for next CPU time. Now, when the process actually requests for next CPU time until the process receive the CPU, actually get the CPU, that's called response time. So in this particular case, once it's quit, and then it's requested for next CPU time in one time unit. So the response time is 1. Now the CPU time is actually 100% because only one process is actually using the CPU. So this process is going to actually completely take 1% of the CPU time. Now, this case is actually, we are talking about two processes. This is one process, and this is two processes. So if you use the time round robin, so supposedly if the time quantum in this case looks like it's 2, right? So now the time, the process actually completed 2 time quantum and switch to next process 2, and process 2 executed for 2 time quantum and then switch back. Now in this case, the process 1 is not using the CPU, but however, since based on the round robin, so this is actually the time quantum which is dedicated to process 1. So the process 2 cannot do it. So this time, so for the first actually one time unit, actually no process is actually using the CPU. But the CPU is allocated to process 1, even though process 1 does not use it. So then the process 1 start to use the CPU again. The total is 2 time quantum, 2 actual time units. And then after time quantum elapse, then process 2 get the CPU. So it's just turning back and forth. Now, because of this, when process 1 complete the first part and then request for next part, so even though the response time is 1, once you send the request to receive the actually CPU, it's 1. But if you have 2 processes, then process 2 will actually take over 2 time units. Okay, so the total response time becomes 3, because when you request the time at the time 2 and get the CPU at the time 5, so the response time is actually 3. Okay, so this is actually the actual response time, and this is actually, it's delayed by the process 2, because process 2 actually takes 2 time units of the CPU. So the total response time becomes 3. Now, this is another case. So we still have two processes, process 1, process 2. However, in this case, you have a context switching. So the context switching time is 1 time unit. So I use red color to represent the context switching time. And the time quantum is still, the time quantum becomes 3. Okay. So the time quantum is 3. So in this case, the time quantum is 2. Context switching time is 0. And this is context switching time is 0. Time quantum, it really doesn't matter because it's always allocated to the process. So I can still say it's 2, right? So, and then, oh, I'm sorry, the time quantum is still 2. Okay. Yes, time quantum is still 2. So then the process 1, run for 2 time units. That's the time quantum. And then it's a context switching time, just for 1 time unit. So even though the time quantum is 2, but the process 2 still waited, until time 3, because it's a time quantum plus the context switching time. And then the process 2 actually run for another time unit, 2 time units. That's the time quantum. And then context switching time. And switch to another one. And then when this process 1 takes up the CPU time, but the process 1 is waiting for it's waiting, right? Because so then it's not actually running in the CPU. And then when the times come, so process 1 start to run, and it only gets 1 time unit because the time quantum is 2. Even though you wasted 1 time unit, but still you're not going to actually get the more actually time because you're still allocated to time quantum. So, and then the context switching time. And then the quantum again, context switching time. So in this case, when you switch back between process 1 and process 2, don't forget the time the context switching time, because this time the context switching actually matters. Okay. Now, in this particular case, we need to actually figure out, there are two actually things you need to actually think about. Now, in the first case, the context switching time is 0, and the time quantum is 2. So the process 1 will continuously use the CPU. So the CPU utilization is, it's called the CPU utilization, it's 100%. Okay. Now, in this case, there's no actually context switching time. This context switching time is ignorable. So the CPU is either allocated to P1 or P2. So the total CPU utilization it's still 100. Okay. However, this 100 is divided among between these P1 and P2. So each process only get 50% of the CPU. So the total CPU utilization is still 100%. But this 100% is divided up between these two. Now, what's the total CPU utilization time in this case? In case 3. Every actually 2 time units, every actually 1 time quantum, which takes 2 units, right? And then you're going to do the context switching. Every actually execute for 2 time units, you take 1 time unit of context switching. So now the context switching is the time used by CPU, but it does not do any meaningful job, right? It's just the overhead. So the context switching takes 1/3 of the CPU time. So the CPU utilization in this case is what? So every two actually useful use of the CPU, 2 time units, and then 1 time unit is just do the context switching. But the context switching does not do any actual job. It's just to actually save the current process into the process control block and then load the next process into the CPU. So it's just actually doing this. Save the current job, load the next job. It does not do any meaningful job. So every actually 2 time units of running the CPU, then the CPU gonna waste it for 1 time unit. So the CPU actually utilization, the total CPU utilization is what? 2/3, right? Because for every actually 3 time units, 1 actually time unit is wasted. So only 2 useful actually use of a meaningful use of time. So 2/3. 2/3 is actually about 60. It's actually 66.666. It's continuous, but I just say it's a 66%. Now this 66% is the total CPU utilization. Okay, 1/3 of CPU time cycle is wasted. However, this 66% is also shared among between these two. So each actually process only get 30% of the CPU time. Now, what is the actual response time for process 1? So process 1 finished the first cycle, first part, and request for the next one. The next one, the process actually 1 cannot get the next one until at the time 7. So when they request at the 2, they get at the time 7. So 7 minus 2, that's 5. Okay, so that's the response time. Now, this case is slightly different. This case, the context switching time is still 1. That's a red color. Okay, that's a context switching time. Now the quantum, the time quantum is 3 now. So basically you're going to execute for 3 time unit. And then you execute, you basically doing the context switching. And then you run 3 time units. And then execute the context switching. And 3 time unit, execute the context switching. So you are actually, the time quantum actually increased. The time quantum becomes 3. So in that case, what's the CPU utilization, total CPU utilization? What's the total CPU utilization? Do I hear anything? Anyone?
So would it be like 3/4 of like 100%?
3/4. Okay. So for every actually 4 time units, every 4 time units, the useful CPU actually time is 3 time units. Only actually 1 cycle is wasted. So you wasted 1 time units for every 4 time units, right? So the utilization is 3/4. So that's 75%. CPU util is 75%. Now this 75% is going to be shared between these two. So 75 divided by 2, so it's 37. It's slight improvement of the CPU utilization. So that means if your time quantum is relatively bigger, than the context switching time, then CPU utilization going to be improved. Okay. So that's basically tell us a story. If your context switching time, the context switching time is fixed because it depends on the performance of the hardware. Because if the computer is very fast, the context switching time can be fast because context switching time only does the job of saving the data for the existing process and load the data for the next process. So that's context switching time. So it's fixed. Now, in this case, the context switch time, we assume the context switch time is one time unit. It doesn't matter what this time unit means. Time unit could be 1 millisecond, it could be 1 microsecond, right? It's one time unit. Okay. So if the context switching time is fixed, then in order to increase the CPU utilization, you have to increase the time quantum, right? You have to increase the time quantum. That way, you're going to increase the CPU utilization. For example, if the time quantum is 2, the CPU utilization is 66%. If the actually time quantum is 3, then it's 75%. Okay. Now, if you continue to shrink the time quantum, so for example, if the time quantum is 1, not 2, and the context switching time is 1, so the time quantum is 1. So that means for every 1 time unit of running, you're going to do the context switching for 1 unit time unit. So basically, it's half and a half. So the total CPU utilization is half and a half. So basically, which means it doesn't matter how fast your CPU is. Half of your CPU time is dedicated on the context switching, which is not doing any meaningful job. Okay, so that's bad. So that means you should actually make the time quantum relatively larger than the time quantum. Okay. Now in practice, for most of the real application, if you use round robin, if the time quantum is 1 time unit, typically, if the context switching is 1 time unit, if the context switching is 1 time unit, now typically the time quantum going to be like a 50 or 49. So the time quantum, the context switching only makes like 2 to 5% of the total CPU time. So that means it's reasonable to assume that if your time quantum is 5, if your actual context switching is 5 time units, then your time quantum should be like somewhere around like 90 to 95. Okay, so time quantum should only be like a 1/3 or 1/10 or 1/20 of the total CPU time. So in that case, the CPU utilization going to be around 90 to 95. Okay. So you have to actually make sure that the context switching time is relatively small compared with the time quantum. Does that make sense? However, if you increase the time quantum to 3, now what is the actual response time? The response time is going to be increased. If you look at this one, start from 2, you start to request for next actually CPU, but when you actually get the next CPU, it's 8. So 8 minus 2, it's 6. So the response time is actually increased. That's the cost for increased CPU utilization. So when you increase the time quantum, the response time increased. That makes sense, right? Because if the time quantum is bigger, then every process is going to take a longer CPU time. So that means for the next process to actually get the CPU, the time period is going to be longer. So that's basically the trade-off. Now let's take a look at the last case. Now in that case, we have a time quantum. Context switching time is still 1. Now the time quantum is still 3. But now you have 3 processes. You have 3 processes. Okay. So the process 1 takes 3 time units, and then context switch. And process 2 takes 3 time units, context switch. Process 3 get 1 time quantum, and then context switch, and then move back to process 1. And now the process 1 get the CPU. Okay. Now let's take a look at the response time. Of course, the response time can be longer because you have more processes, right? So you got the you request for the CPU at the time 2, and you got the CPU at the time 12 because you have 2 processes in between, plus the CPU the context switching time. So you normally have a two time quantums because of the 2 additional processes running. 2 time quantum plus 3 context switching in between. So you have a 3 context switching plus 2 time quantum. Now the context switching is 1. So 3 times 1 is 3. And time quantum is 3. So 2 times 3 is 2 times 3 is 6. So total is 9. Plus its own waiting time. So the total response time is 10. So that's internal. That's the process 1's waiting time for the next CPU burst. And that's basically the time wasted on the other 2 processes. Okay. So in this particular case, the total CPU utilization is still 75 because you have a 1 context switching time versus 3 time quantum. So 3 time quantum versus 1 context switching time. So that's actually 3 out of 4. So the CPU utilization is still 75. However, this 75 is shared by 3 processes. So each process only get 25% of the CPU time, 1/4 of the CPU time. That's expected, right? If you increase the number of processes, then each process gonna get fewer and fewer CPU time. It's a little complicated than the FIFO or shortest job first or the shortest remaining time first, But, this is actually how you're going to actually calculate the performance of the time, for the time sharing, the round robin. Okay. Now let's take a look at the example. Okay. So let's actually take a look at this. I think this example is actually, I just pull out the example from one of the exercises in the Xi book. So let's suppose that we have 11 processes. 11 processes are executing using round robin scheduling. Okay. So the context switching time is 1. So S is 1, context switching time. Now, this problem is a little bit of it's not straightforward. No, so it requires some actual thinking. Now let's say determine the maximum quantum size Q such that the gap between the end of the process PI's quantum and the start of the PI's next quantum does not exceed 41 time units. Okay, now let's see. Process 1, process 2, process 3, 4, 5, process 11. So it asks you to actually calculate what is the time quantum. Okay, so process 1 get 1 time quantum, right? And then context switching, which is 1. And then move to process 2, get a 1 time quantum, and the context switch is S1, S, which is 2, is also 1. And then So the last one is process time quantum plus the context switching. So once after just one cycle for 11 process, then the CPU going to be back to the process 1, right? And the context switching. Now the question is, determine the maximum quantum size Q such that the gap between the end of the process PI, let's say instead of PI, I'm going to use P1, okay? I can say I use P1. You can use P2, that's okay. For P1, now for P1, what's the end of the process P1's quantum? So this is a 1 quantum. The end of this quantum is actually here, right? That's the end of the quantum. And then you have a 1 context switching. And then another quantum, context switching, another quantum, context switching, another quantum, context switching. So between the end of the process PI's quantum and the start of PI's next quantum. What's the start of next quantum? That's the start of next quantum. So that's the end of the current time quantum. That's for P1. Now, if we use P2, that's okay. So for P2, the end of the current quantum is here, right? The start of the next time quantum going to be here. Okay. So basically, that's the total time between the end of the current time quantum and the start of next time quantum. Now, what the problem says, between here and here, what's the value? It's 41, right? That's basically. So if you use P1, that's the gap between the end of the process 1's quantum and then the next quantum. And if you use P2, now that's the end, and that's the next one. It's also, there's no difference because the P2 is just the shift of 1 time quantum plus the context switching. So you use this one, that's also 41. Doesn't make any difference. So I use P1. Okay. Now, so let's see. You have 41. Now 41 equals what? we want to find what's the Q, right? So how this is actually how this can be adding up. So how many actually context switching between this one and this one? How many context switching?
11.
1, 2, 3, 4, all the way to here. That's 1, 2, because that's total of 11. So from P2 to P11, that's total of 10, right? And 10 context switching. Now plus this one. So you have total of 11 context switching. So one context switching, one context switching, one context switching. That's total 11. Now how many time quantum? So that's total 11 process. Now between this here, you have the time quantum for P2, time quantum for P3, time quantum for P4, and P5, and the last one is P11. So that's from here to here. That's total of how many time quantum? 10, right? Any questions on this? So these 11 context switching plus 10 time quantum, that's total of 41. Now you know the context switching is 1, so you can replace S with 1. Okay, so now you have 40. So I can basically replace these, replace S with 1. That's a context switching. Now what is Q? So you have a 41 equals 11 times 1 plus 10 times the Q. So what is the value of Q?
3.
Okay, so this is actually, you're going to solve the problem that way. Any questions? So this is how you're going to actually figure out how to calculate the time quantum, and so this is somehow related to the performance. So to the end of the current quantum to the beginning of the next quantum, that's you have the total number of time quantums for the other process plus the context switching. Okay, so typically if you have n processes, okay, so that means this time between actually between the end of the current time quantum to the beginning of the next time quantum, it's basically a n times the context switching time plus n minus 1 times the time quantum. So that's the time between the end of the current process, current actually time quantum to the beginning of next time quantum. Okay. Now in this particular case, n is 11, so it's 11 times the context switching plus 10 times the time quantum, and the condition says, does not exist 41. So then you can say assume it's 41. Okay. Okay, I'm gonna move to the next slide. Do you have any questions on this one? Now here's another example. Okay. So I'm gonna actually do two examples. Now in this case, I have 3 processes. Process 1, 2, 3. It's also interactive scheduling, so that means it's round robin I'm going to use. Okay, so process 1 arrived at time 0, process 2 arrived at time 0, but process 1 arrived a little bit earlier than process 2, even though they arrive at approximately the same time. Now, the total CPU time, okay, so that 7 should be here. 70, 20, 10. Okay, so I just shifted it. So the total CPU time is 70, 20, and 10. And oh, this is actually for the multi-level feedback queue. Okay, so that's interesting. So there are 3 processes following arrival times, and the total CPU times are executed using the multi-level feedback scheduling. Remember, multi-level feedback scheduling is just like this. So initially, the process is going to be placed on the top level, queue, which has a small time quantum, and then if one time quantum cannot finish the job, the remaining part of the work going to be switched to the next level of the queue, and then executed with a double time quantum. So that's so let's do that. So you have 5 priority level. So level 5, level 4, 3, 2, and 1. Okay. Now the time quantum is Q. The time quantum Q is 10. Okay, at the level 5. So Q is 10 at the level 5, and it doubled at each lower level. So now the Q is 20. So it's actually 2Q, which is 20. And the lower level doubles again. So it's a 4Q, 40. Okay. Now this level 2, it doubles the previous one. So it's 8Q, which is 80. And 16Q, which is 16. 160. Okay. So it's a 1, a 10, 20, 40, 80, 160. So this is a high priority, queue, and this is next highest priority, and this is next highest priority. Okay. Now assume the context switching time is 0. Okay, so there's no context switching time. So the question is, which priority level does P1 terminate at? Now to do this question, I think what I can do is I have a process 1, process 2, process 3. Okay, now this is a time. When process 1 arrives, the process 1 will be placed in the highest level queue, right? So it's going to, because the process 1 is the only process which is currently available. So the process 1 going to start to execute. Okay, with 1 time quantum in level 5, right? In level 5. Now, when process 1 complete the job, not complete the job, and a complete 1 time quantum, so there's a 60 actually CPU time remaining, but the process 1 going to be placed in the level 4. Okay. So, and then process 2 actually arrives. So process 1 just completed it. When process 2 arrives, it has, so based on the multi-level feedback queue, as far as you have a process in the highest level, highest priority queue, then process 2 going to get the CPU, right? And it just run another time quantum. It's a queue. Okay. Now, when process 2 finish the job, so this is 0, 10, 20, right? So each queue is actually 10. So you have 2 actual time quantity, that's 20. So 20, when process 2 finish 10, so process 2 going to be actually placed at the back of the level 4 queue. So at this moment, there are only 2 processes because process 3 hasn't arrived yet, right? Process 3 hasn't arrived yet. So then in this case, who's going to get the CPU first? Process 2 going to get the CPU. Process 1 going to get the CPU because process 1 already actually in the level 4. So now process 1 run for 10 time units at the 30. Now why I stop here? Because here there's only 1 time quantum. Okay, so let's see. There's only actually, the time quantity is 20, but it should actually run for actually from 20 to 40, right? Because the time quantity is 20, so you need to run actually 20 time units. However, process 3 arrives at the 30, right? So now process 3, once the process 3 arrives, it will be placed in the highest level queue. In the highest level queue. So that's the reason why you're gonna immediately interrupt the process 1, and so process 3 gonna be in the queue. Okay. So process 3 in the level 1. Okay. So that's also level 1. And this is actually level 2 or level 4 for process 1. Now when process 1 finish at the level 5 for 10 quantum, 10 actually time units. Oh, I'm sorry, not 10 quantum, 10 time units. Process 3 is actually just 10 time units. So it's actually completed job. It's not going to actually put it in the level 4 because it's done. Okay. So now you go back and process 1 continue to finish the remaining one in level 4 for another actually 10 time units. So it's once it's done, so now the process 1 has completed 10 time units and 20 time units because in level 2 it completed 20 time unit. So there's still actually 40 time units remaining, right? So the process 1 going to be placed in level 4 or level 3. And then the process 2. Process 2 is the highest priority now. So process 2, it has to actually complete the 1 time unit, and there's a 10 remaining. So process 2 going to be running for 10 time units in level 4, right? And then process 1 completed remaining job in level 3. Okay, it's actually 40. So that's 50, and then the 40 again 90. Yeah, so that's a 10, 20, 30, 40, 50. I think it's a 50. 60. Okay. So then 100. So that's in level 3, total of 40, 60 to 100. That's total actually 40 remaining. Okay, 40 remaining. So you can actually do the job. So now the question is, which priority level does P1 terminate at? Here, right? So that's level 3.
Professor, I have a quick question.
Yes.
For P2, should those be, or P2 and P3, should those be level 5? The first quantum on each? Because they say level 1 on them.
Yeah, P2 is actually the CPU times 20, right? So it's in level 1, it only executed 10 time units. So you still have 10 time units left. So the P2 should be placed in level 4. Do I answer your question?
No, I was sorry. I was more saying that it's labeled as level 1 when they're starting at level 5.
Oh, sorry. Level 5. And also level 5. That's correct.
Thank you.
Yeah, I'm thinking level 5 is the highest priority, so it should be placed initially. So yeah, initially should be put in the level 5, and then level 4, and then level 3. So yes, thank you. So P1 terminates at the level 3, right? Now what about the P3? P3 terminates at actually P3 actually is a very short process, so it's actually completed in level 5, right? It never actually moved down to level 4, so it terminates at level 5. And what is the turnaround time for P1? P1 actually start first, and P1 actually end at the very last minute. So the turnaround time for P1 is 100, right? And what is the turnaround time for P3?
40.
P3 actually get the, enter the ready queue at the time 30, right? But immediately get the CPU. So complete at the 40. So it's 40 minus 30 is a 10. Does that make sense to you?
Yes.
Yes. Okay. Now what about P2? P2 actually complete at here. That's 60. So it's actually start from 0. So P2 is actually 60. The turnaround time for P2 is 60. Okay. So now I think this Gantt chart, the chart is very useful. So every time when you actually answer the questions like this, and I recommend to use the chart, because otherwise you're going to be confused. You're going to mess up all these things. Okay. And now I think we're running out of time, but scheduling for real-time process. Now we only have time to talk about what the real-time process is. Now real-time process is, it's a very important processes, because it's a real-time process. Once the process requests for CPU, there's a hard time limit for the process. Now, if you get the CPU before that time period, that's okay. Now, if you actually say, I want the CPU within like 5 seconds, then if you miss the 5 seconds, then the whole thing fails. The other actually scheduling algorithm, like a real first in, first out, and Fifo, shortest job first, and these are called best effort. So as far as you have a priority for each of the processes, if they are not real time, so I only just follow the rule and say you're the first, you're the second, you're the third. And the real time is different. Real time says if I request for CPU, I have to get the CPU within a certain period of time. Now this is very important, particularly if you talk about the software running on the Tesla vehicle, or you are actually operate an airplane. It's so it's a fly-by-wire. So you have the gears, and you basically actually operate the vehicle, operate the airplane to actually take off or land. So you actually perform any operation, you have to actually make sure the machine going to respond and complete the operation within certain period of time. And this is a hard actually time limit. So there's no negotiation. Say, so I'm sorry, I have too many processes actually around. I cannot, get the job done within 5 seconds. Can you do this within 7 seconds or 10 seconds? The answer is no, because if that's the case, now if your vehicle is supposed to turn right, then you cannot do these operations, and then you will end up like not turning right. You actually end up turning into a river, not turn right. So that's called the real-time process. The real-time process, the scheduling algorithm is kind of different. Okay. We're going to talk about real-time operations, real-time scheduling, but I think I'm not going to include this in the test, in any of the tests, or even so the real-time actually process is kind of tough. Okay, the scheduling is kind of tough to do this. There's a chance that real-time actual schedule is going to fail. Okay, I think that's pretty much all for today. And so I'm gonna actually post some of the information about the test, and the test is gonna be, as I said, it's March. Let me see, it's next Thursday. So if you have any questions, actually, you can still ask on next Tuesday. Okay, so if you actually work on the assignments and you have problem, you have a question, just ask me. Or if you actually have a problem during the weekend, you can just email me. Okay, and I think I'm always available. Okay, so tomorrow I'm going to be temporarily off the screen. So if you ask a question tomorrow, I may not be that responsive, but I'm definitely going to be back on Saturday. Okay. Okay. That's pretty much all for today.